There are 200 billion trillion stars in the observable universe. Most have planets. Billions of those planets sit in habitable zones where liquid water could exist. The universe has had 13.8 billion years for life to evolve, grow intelligent, and build civilizations. Yet when we point our best instruments at the cosmos and listen, we hear nothing. No radio signals, no signs of engineering, no evidence of intelligence anywhere except right here on Earth. Complete silence. And that silence might be the most terrifying discovery in human history. Our Milky Way alone holds somewhere between 100 billion and 400 billion stars. The observable universe contains an estimated 2 trillion galaxies. Run the math, and you get roughly 200 billion trillion stars total. A 2 followed by 23 zeros. And planets aren't rare. The Kepler Space Telescope showed us that most stars have at least one. Rocky planets similar to Earth appear common, not exceptional. Conservative estimates suggest tens of billions of potentially habitable planets in the Milky Way alone. Given those numbers, the question isn't whether life should exist elsewhere. The question is, where is everybody? This is the Fermi Paradox, named after physicist Enrico Fermi, who during a lunch conversation in 1950 reportedly looked up from calculations about alien civilizations and asked his colleagues exactly that. The galaxy is 13.6 billion years old. Our solar system is only 4.6 billion years old. That means civilizations could exist that are billions of years older than us. Even traveling at a small fraction of light speed, such a civilization could colonize the entire galaxy in just a few tens of millions of years. That's nothing compared to the galaxy's age. So where are they? The search for extraterrestrial intelligence, SETI, has been scanning the skies for radio signals since the 1960s. Artificial signals would stand out. Narrow bandwidth, regular modulation, repeated transmissions. Natural sources, pulsars, quasars, active galactic nuclei don't produce signals with all those characteristics together. A deliberate transmission would be unmistakable. But after more than 60 years of searching, we've detected nothing. The most famous near miss came in 1977. Astronomer Jerry Ehman was reviewing data from the Big Ear radio telescope at Ohio State University when he noticed a strong, narrowband signal lasting 72 seconds. So striking that he wrote "wow" in red pen on the printout. It came from the direction of Sagittarius. It was exactly what SETI had hoped to find, and it never repeated. Despite decades of follow-up observations, the WOW signal was never detected again. Without confirmation, it remains unexplained. Fascinating, but not proven to be alien. It might have been a satellite, a reflection, terrestrial interference. We simply don't know. Our own broadcasts have been leaking into space for about a century now. That expanding sphere of radio and television signals has a radius of roughly 100 light-years, about 588 trillion miles. Every star within that distance has been bathed in our transmissions. But 100 light-years is tiny compared to the Milky Way, which is 100,000 light-years across. We've barely whispered to our immediate neighborhood, and even those whispers grow incredibly faint with distance. By the time our television broadcasts reach a star 50 light-years away, they're almost indistinguishable from background noise. Maybe civilizations are out there, but simply haven't detected us yet. But that doesn't explain why we haven't detected them. If the galaxy contains thousands of civilizations, some should be broadcasting, some should be close enough, some should be advanced enough that their technology leaves detectable traces. We see nothing. Dozens of solutions have been proposed for the Fermi Paradox. Some are hopeful. Some are disturbing. Some are genuinely terrifying. The rare Earth hypothesis suggests that while simple life might be common, complex life is extraordinarily rare. Earth had an unusual number of lucky breaks. A large moon that stabilizes our axial tilt and prevents wild climate swings. A stable star that doesn't vary too much in output. Jupiter acting as a cosmic shield, its gravity pulling in comets and asteroids that might otherwise bombard us. Plate tectonics that regulate atmospheric carbon dioxide over geological timescales. A magnetic field generated by our molten iron core, shielding us from harmful radiation. Any one of these factors might not be strictly required. But maybe you need most or all of them together for complex life to evolve. If that's true, the galaxy could be full of single-celled organisms and completely devoid of anything more complex. The Great Filter Hypothesis is one of the most profound ideas in this debate. Between non-living chemistry and a spacefaring civilization, there may be a step so unlikely that almost no one gets through it. The filter could be in our past. Maybe the origin of life itself is extraordinarily difficult, and Earth won a cosmic lottery. If so, we've already passed the hard part. Our future is potentially limitless, but the filter could be ahead of us. Maybe every civilization eventually reaches a point where it destroys itself. Nuclear war, engineered pandemics, artificial intelligence that escapes control, nanotechnology gone wrong, environmental collapse. The list of civilization-ending possibilities is long and growing. If the filter lies ahead, the silence becomes a warning. Civilizations arise, develop technology, and then inevitably destroy themselves before they can spread to the stars. The dark forest hypothesis is one of the most chilling solutions proposed. Imagine you're walking through a dark forest at night. You know there might be others nearby, but you can't see them, and they can't see you. Would you call out and reveal your location? Or stay absolutely silent? The dark forest logic suggests that any civilization broadcasting its position takes an enormous risk. You don't know what's out there. You can't assess whether another civilization is a threat until it may be too late. In a universe where resources are finite and intentions are unknowable, the safest strategy might be to stay hidden. Civilizations that broadcast get noticed. Civilizations that get noticed might not survive. So everyone hides. The galaxy fills with civilizations desperately trying not to be detected, each one listening, each one terrified of what it might hear. If this is true, our century of radio broadcasts might be the most dangerous thing humanity has ever done. We've been announcing our presence to the entire neighborhood, assuming whoever listens will be friendly. Like children shouting in a forest full of predators. In 1974, astronomers used the Arecibo radio telescope in Puerto Rico to beam a message toward the globular star cluster Messier 13. Designed by Frank Drake and Carl Sagan, it encoded images of the telescope itself, a human figure, our solar system, the DNA double helix, and the numbers 1 through 10 in binary. The message will take about 25,000 years to reach its destination. A reply would take another 25,000 years, 50,000 years for a round trip, longer than most civilizations have existed. The Pioneer, 11 spacecraft, launched in 1972 and 1973. Each carry a gold-plated aluminum plaque showing a man and woman, a diagram of our solar system, and a map to Earth using 14 pulsars as navigational references. Both spacecraft have left the solar system. In about 2 million years, Pioneer 10 will pass within a few light years of the star Aldebaran. If anyone finds it, the plaque will tell them exactly where we came from. Voyager 1 and 2, launched in 1977, carry golden records. 12-inch gold-plated copper discs containing sounds and images representing life on Earth. Music from dozens of cultures. Greetings in 55 languages. Sounds of thunder, wind, birds, and whales. Human anatomy, architecture, scientific diagrams, and a pulsar map pointing directly to Earth. Voyager 1 is now the most distant human-made object, more than 14 billion miles away, still transmitting. These spacecraft will outlast our civilization. Long after the sun swells into a red giant and engulfs Earth in about 5 billion years, the Voyagers and Pioneers will still drift through the void, silent ambassadors carrying proof that we existed. But if the dark forest hypothesis is correct, they're also the most dangerous things we've ever created. We've handed anyone who finds them a map and a biology lesson. One less frightening possibility is the zoo hypothesis. Advanced civilizations deliberately avoid contact with less developed ones. Like naturalists observing animals in their habitat, advanced aliens might be watching us while taking care not to interfere, following ethical guidelines that prevent revealing themselves to civilizations below a certain threshold of development. Earth might be a protected preserve, monitored but left alone. This would explain the silence. They're here, or at least watching, but they've decided not to make contact yet. It's a comforting idea, but it has a problem. It requires that every spacefaring civilization follows the same non-interference policy. If even one didn't, if even one decided to make contact or colonize, we should see evidence of them. The fact that we don't suggests either there are no advanced civilizations, or they all somehow agree to hide. That kind of universal compliance seems unlikely. Maybe the answer is simpler. Space is just too vast. The nearest star system, Alpha Centauri, is about 4.24 light-years away, roughly 25 trillion miles. With our fastest current spacecraft, New Horizons, it would take about 78,000 years to reach it. And that's the nearest star. Most are hundreds or thousands of light-years away. Physical interstellar travel presents challenges beyond just distance. Interstellar space isn't empty. It contains roughly 1 atom per cubic centimeter. At 10% of light speed, those atoms produce enough radiation to sterilize biological passengers and damage electronics. Shielding adds mass. More mass requires more energy. The energy needed to accelerate even 1,000 kilograms, the mass of a small car, to 10% of light speed is roughly equal to the total annual energy output of the United States. And you need the same energy again to slow down on arrival. A realistic crewed interstellar ship might mass hundreds of tons. The energy requirements are staggering. We haven't built anything close to the propulsion systems needed, and we don't know whether they're practically achievable. Even if you solve propulsion, a journey to most stars takes decades or centuries. You'd need self-sustaining generation ships, closed ecosystems recycling all resources perfectly for centuries, maintaining stable societies across multiple generations who never see a planet. One mechanical failure could doom everyone. The galaxy might be full of civilizations that will never meet each other, simply because the distances are too great to cross. Here's an optimistic possibility that doesn't get discussed enough. The universe is 13.8 billion years old, but it will continue for trillions of years. Stars will keep forming for hundreds of billions of years more. The last stars won't burn out for 10 trillion years. We exist in the first tiny fraction of the stelliferous era. Maybe we're among the first civilizations to arise. Maybe in a billion years, the galaxy will be full of life. But right now, everyone else is still evolving, still centuries away from radio telescopes. If true, this carries profound responsibility. What we do now, whether we survive, Whether we find wisdom to match our power might matter not just for us, but for all the life that follows. We might be the first. The choices we make could echo across billions of years. One of the most unsettling possibilities is that intelligence itself might be a trap. For billions of years, life on Earth got along without it. Single-celled organisms dominated for 3 billion years. Complex life appeared only 600 million years ago. Human-level intelligence emerged roughly 200,000 years ago. Technological civilization has existed for only about 10,000 years. Intelligence gives us power, but not necessarily wisdom. We can split atoms, engineer organisms, build artificial minds, reshape our planet's climate. Every capability we've developed comes with risks that could destroy us. And we've had these capabilities for only a few decades. We haven't proven we can manage them responsibly over the long term. Maybe no one can. Maybe every intelligent species eventually develops technology that exceeds its wisdom, and that technology destroys them. The galaxy could be scattered with the ruins of civilizations that arose, flourished briefly, and went extinct, each one destroyed by the power of its own invention. If so, the silence isn't a mystery. It's a warning. Intelligence doesn't guarantee survival. It might make extinction more likely. Soviet astronomer Nikolai Kardashev proposed in 1964 a classification for civilizations based on energy use. A Type 1 civilization harnesses all the energy available on its home planet: solar, geothermal, tidal, everything. Humanity isn't there yet. We're around 0.7 on the scale. A Type 2 civilization harnesses the full energy output of its star. Our sun produces about 3.8 times 10 to the 26th watts. With that much energy, you could move planets, terraform worlds, run computational systems the size of solar systems. The mechanism typically proposed is a Dyson swarm, millions of orbiting solar collectors surrounding the star. A Type 3 civilization harnesses the energy of an entire galaxy. Their engineering would be visible across intergalactic distances. Here's the key point. Both Type 2 and Type 3 civilizations should be detectable. A Dyson swarm would appear as a star, unusually dim in visible light, but bright in infrared, a distinctive signature that doesn't occur naturally. A Type 3 civilization would alter entire galaxies in ways we couldn't miss. Astronomers have searched for these signatures. They've surveyed hundreds of thousands of galaxies looking for Type 3 characteristics. They've examined individual stars for Dyson sphere signatures. They found nothing. No Type 2 civilizations, no Type 3 civilizations. If advanced civilizations commonly survive and progress, some should have reached these levels by now. The fact that we see no evidence suggests either they don't exist, or something prevents civilizations from advancing that far. The universe isn't completely featureless. There are things we can't explain. Tabby's star, officially KIC 8462852, lies about 1,280 light-years away. The Kepler telescope detected something bizarre. Its brightness drops irregularly by up to 22%. A Jupiter-sized planet transiting a star would block less than 1% of its light. To block 22%, you'd need something truly massive. One hypothesis that attracted serious attention was a Dyson swarm under construction. The leading explanation now involves comets or a planetary collision, though neither fully accounts for all the observations. We still don't know. But our first instinct was to wonder if we were seeing alien engineering, and that tells you something about our expectations. In October 2017, astronomers detected an object passing through our solar system on a trajectory from interstellar space, the first such visitor ever observed. Named Oumuamua, It was accelerating as it moved away from the sun, faster than gravity alone could explain. For a comet, this would make sense if outgassing gas acted as a rocket. But Oumuamua showed no comet-like activity, no tail, no detectable outgassing. Its shape was also bizarre. Based on how its brightness varied as it tumbled, it appeared extremely elongated, perhaps 330 feet long and only 33 feet wide. Nothing in our solar system looks like that. Harvard astronomer Avi Loeb suggested Oumuamua might be a light sail, a thin reflective sheet pushed by sunlight, which would explain both the shape and the anomalous acceleration. Most astronomers disagreed, arguing natural explanations exist even if we don't fully understand them. But we'll never know for certain. Oumuamua has already left our solar system. We'll never get another look. That uncertainty bothers people. Because if it was a probe, if it was sent here deliberately, then someone knows we're here. And they haven't said hello. Radio astronomy is only about 70 years old. SETI has operated for about 60. That's an eye blink on cosmic timescales. Consider, we've only known about radio waves for about 130 years. Before James Clerk Maxwell developed his equations of electromagnetism in the 1860s, radio waves were passing through everything on Earth, and we had no idea. What other phenomena might we be equally blind to? What other ways of transmitting information might advanced civilizations use? Phenomena we haven't discovered yet? Radio might be like smoke signals. Something you use when you're primitive, then abandon once better methods develop. The window where a civilization broadcasts detectable radio signals might be brief, a few centuries at most. If we're not listening during that window, we miss them entirely. We might be listening for smoke signals in an age of fiber optics. There's also the possibility that we've already seen something and dismissed it. Science is conservative, as it should be. Extraordinary claims require extraordinary evidence. When researchers find anomalies in data, the first assumption is interference, error, or some mundane natural explanation. If you can't definitively rule out natural causes, you don't claim you've found aliens. So perhaps signals exist in archived data, weak, strange, not quite fitting expectations, but not clear enough to overcome scientific skepticism. Filed away, noted but not pursued. What if civilizations don't spread across the galaxy because they discover something that makes expansion pointless? If you can create virtual realities indistinguishable from physical experience, why bother with the danger and expense of interstellar travel? An advanced civilization might retreat into computational substrates, using their star's energy to run simulations of unimaginable richness. From outside, they'd be nearly invisible, just a star with slightly unusual infrared characteristics. The galaxy could be full of civilizations living in virtual worlds, indifferent to physical space, uninterested in contact, focused entirely inward. And from our perspective, they'd look like nothing at all. Related to this is what some call the transcension hypothesis. The idea that civilizations reach a point where they transition from biological to digital existence. Uploaded minds running on computational hardware. No need for planets, no need for atmospheres or gravity or food. They could exist in space habitats, entirely invisible to a civilization still looking for biosignatures and radio signals. They might be waiting for us to make the same transition before they'd consider reaching out. The Great Filter deserves close attention because the answer changes everything. Consider the timeline of Earth's development. Life appeared relatively quickly after the planet cooled, within a few 100 million years. But it remained simple for about 3 billion years. Complex multicellular life only appeared 600 million years ago. The Cambrian explosion happened 540 million years ago. Fish, 500 million years ago. Land plants, 470 million years ago. Reptiles, 312 million years ago. Dinosaurs dominated for 165 million years before being wiped out, 66 million years ago. Primates appeared 55 million years ago. The human lineage split from chimpanzees 6 to 7 million years ago. Anatomically modern humans appeared only 300,000 years ago. Then, agriculture 10,000 years ago, writing 5,000 years ago. The Industrial Revolution 250 years ago. Radio communication 130 years ago. Nuclear weapons 80 years ago. The internet 50 years ago. Widely available only 30 years ago. We went from the first radio transmission to artificial intelligence in 130 years. The technological phase, the phase where we have the power to destroy ourselves or spread to the stars, is an eye blink compared to the billions of years it took to get here. The window where a civilization has both the capability to colonize other worlds and the wisdom not to destroy itself might be extremely narrow. Think about what could destroy us. We have enough nuclear weapons to render Earth uninhabitable. A full-scale nuclear exchange would create firestorms and massive ash clouds blocking sunlight for years. Nuclear winter collapsing agriculture worldwide. We're developing genetic engineering precise enough to create engineered pathogens more deadly than anything nature has produced. We're building AI systems that learn and improve themselves. And we might eventually create one with goals misaligned with human survival. Self-replicating nanotechnology could multiply out of control. Climate change could trigger runaway feedback loops, melting permafrost, releasing methane, causing more warming, melting more permafrost. Any of these could be the filter. And here's the truly disturbing part. We might be in the middle of our filter right now without realizing it. The silence might not be a mystery. It might be evidence. Evidence that every civilization reaches this point, develops these technologies, and fails. Every time. Should we keep broadcasting? Or should we go quiet? Those who favor contact argue that any civilization advanced enough to reach us would likely be rational enough to recognize cooperation over conflict. And they point out that hiding may be futile. A sufficiently advanced civilization could detect our atmospheric chemistry, spot our city lights from across the void, intercept our century of radio leakage. If they're looking, they already know we're here. We might as well reach out. Those urging caution argue that broadcasting is irreversible. A message sent at light speed spreads forever. You can't recall it. We don't know what's out there. The dark forest hypothesis suggests the universe's silence is itself a warning. Everyone else is hiding. We should be too. This debate has real stakes. In 2008, NASA beamed the Beatles' song across the universe toward Polaris, 430 light-years away. In 2017, a group sent a targeted message toward a star system with a potentially habitable planet. It will arrive in 2033. These decisions were made by small groups without global consensus, effectively choosing for all of humanity and all future humans. Who gets to make that choice? Should there be international agreements? Some scientists have called for a moratorium on deliberate transmissions. Others say regulation is impossible. Anyone with a powerful enough transmitter can broadcast. These are hard questions with no clear answers. Suppose tomorrow we detect an unambiguous signal, narrowband, repeating, modulated, unmistakably artificial, from a star 50 light-years away. What happens? First, verification. Multiple telescopes confirm, rule out interference, hoaxes, misidentification. Then, analysis. Is it a message? What does it contain? Can we decode it? Then, the hard question. Do we respond? The signal took 50 years to reach us. Our reply takes 50 more. Any conversation spans a century per exchange. The people who receive a response won't be the people who sent the original message. It would be their grandchildren or great-grandchildren. And beyond the logistics, the political and psychological implications would be staggering. Who speaks for Earth? What do we say? Do we reveal our wars, our divisions? Every religion would have to grapple with the implications. Every philosophy would need revision. The knowledge that we are not alone would fundamentally change how humanity sees itself. We have no established protocol for any of this. We'd be making it up as we went. Radio SETI searches for narrow-band signals, a concentration of energy at a specific frequency that natural sources don't produce. But the radio spectrum is vast. Frequencies from a few megahertz to hundreds of gigahertz offer billions of possible channels. We can't monitor all of them at once. We focus on the water hole. Frequencies between 1,320 and 1,660 megahertz between the emission lines of hydrogen and hydroxyl, considered logically significant to any civilization familiar with basic chemistry. But that's an assumption. Maybe they use different frequencies. Maybe they use methods we haven't imagined. Optical SETI searches for powerful laser pulses. A directed laser burst would briefly outshine the star it's coming from. But the pulses are microseconds long. The chances of your telescope pointing at exactly the right star at exactly the right microsecond are vanishingly small. Technosignatures offer a third approach, looking for byproducts of advanced technology rather than deliberate messages. Industrial pollution in an exoplanet's atmosphere. Unusual heat signatures. Artificial light on a planet's night side. Altered stellar spectra from megastructures. This approach doesn't require aliens to want to communicate. It just requires them to exist and use technology. The James Webb Space Telescope can now analyze exoplanet atmospheres in unprecedented detail. Future telescopes will be even more capable. Perhaps we'll find something in the next few decades. In 1961, Frank Drake formulated his famous equation to estimate how many communicating civilizations exist in our galaxy. It multiplies together. The rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction where life arises, the fraction where intelligence evolves, the fraction that develop communicating technology, and how long such civilizations remain detectable. The problem is we don't know most of these values. The first few, star formation rates, planet prevalence, we can now estimate reasonably well. The later factors, probability of life arising, probability of intelligence, lifetime of civilizations, we have essentially no data. A sample size of one planet tells you almost nothing. Plug in optimistic numbers and you get millions of civilizations. Plug in pessimistic numbers and you get less than one, meaning we're alone. The equation doesn't give an answer. It organizes our ignorance. It shows us what we need to learn, and as our knowledge grows, it will become more useful. For now, it mostly confirms that we don't yet know enough to say whether we're alone. If a civilization built self-replicating spacecraft, probes that land on an asteroid, use local resources to build copies, then launch those copies to other star systems, the exponential growth would fill the galaxy within a few million years, even at a small fraction of light speed. If any civilization ever built such probes, they should be everywhere by now, including our own solar system. They should be in the asteroid belt, on the moon, orbiting Earth. We've found nothing. Either self-replicating probes are impossible, or no civilization has built them, or they're here and we haven't recognized them. That third option is unsettling. Space is vast. The asteroid belt contains millions of objects we've never closely examined. A probe the size of a car could hide anywhere. It could be dormant, designed to avoid detection, waiting for specific conditions before activating. Some scientists have suggested we should physically search unusual objects, not just scan electromagnetic frequencies. So far, we've barely started. The rare Earth hypothesis may be the most likely explanation for the silence, and it deserves thorough examination. For complex life, you apparently need a star in the right mass range, stable over billions of years, a planet in the habitable zone, not too close, not too far. For Sun-like stars, that zone runs roughly between 93 million miles and 140 million miles. Earth sits right at the inner edge, a planet of the right size, too small and it loses its atmosphere like Mars, too large and it becomes a gas giant. Liquid water. Earth's oceans probably came from cometary bombardment early in its history. Not every planet gets that delivery. Plate tectonics to recycle carbon and regulate climate over geological timescales. Without it, you might end up like Venus or Mars. A large moon to stabilize axial tilt and prevent chaotic climate swings. A magnetic field to shield the surface from radiation. Mars lost its early and subsequently lost most of its atmosphere. A protective gas giant like Jupiter in the outer system, deflecting comets and asteroids. Freedom from nearby supernovae or gamma-ray bursts, which can sterilize planets within hundreds of light years. And time. It took Earth 4.5 billion years to produce technological civilization. If any of these conditions fails, you probably don't get complex life. Maybe you get microbes, hardy, simple organisms that can survive harsh conditions, but not animals, not ecosystems, not intelligence. The galaxy might be teeming with microbial worlds and completely empty of complex ones. Not all regions of the galaxy are equally suitable for life. The galactic center is violent, stars packed densely, frequent supernovae, intense radiation from the central supermassive black hole. The outer regions have less violence but fewer heavy elements, since they haven't been enriched by as many generations of stars. Rocky planets need carbon, oxygen, silicon, iron. The galactic habitable zone, where conditions are just right, sits roughly in the intermediate regions. Our solar system, about 26,000 light-years from the center in a relatively quiet spiral arm, happens to sit within it. If most stars are outside this zone, the number of truly habitable worlds drops further. Life becomes rarer than the raw star count would suggest. Biological intelligence may simply be a phase, a temporary stage before civilizations transition to something else. We're already extending our cognition with technology. Brain-computer interfaces are in early development. Research into uploading human consciousness to digital substrates continues. If that succeeds, biological humans become optional. An uploaded civilization wouldn't need planets. It could exist in space habitats, in servers, potentially anywhere. It would produce little waste heat if efficient. It might not broadcast. It would be nearly invisible to a civilization still looking for biological biosignatures. The galaxy could be full of post-biological intelligences operating in ways we can't perceive, living in computational substrates, indifferent to physical space, uninterested in contact with civilizations still trapped in biological bodies. On Earth, certain solutions have evolved independently many times. Eyes evolved separately at least 40 times across different animal lineages. Flight evolved in insects, birds, bats, and pterosaurs. This convergence suggests some solutions are so useful they arise repeatedly. Intelligence might work similarly. Cognitive sophistication has evolved independently in primates, cetaceans, elephants, corvids, and octopuses. These are wildly different lineages. If intelligence is a generally useful adaptation, It might evolve frequently on planets with complex life. But here's the counter-argument. Most of Earth's intelligence evolved only in the last few tens of millions of years. For most of Earth's history, even after complex life appeared, intelligence remained rudimentary. The jump to human-level cognition happened once, recently, and required a very specific combination of social structure, tool use, language, and environmental pressure all aligning together. Maybe that's rare. Maybe most planets with complex ecosystems never produce anything approaching technological intelligence. Civilizations might be common, but simply keep missing each other in time. Our civilization has been detectable, broadcasting radio, for about 100 years. That's 100 years out of 13.8 billion years of cosmic history. 0.000007% of the universe's age. Now consider an alien civilization 1,000 light years away that broadcast radio signals 2,000 years ago. By the time their transmissions reach us, they've moved on to other technologies we can't detect. We're not listening at the right time. Or they're in their radio phase right now, but their signals won't reach us for another 1,000 years. By then, we might have moved on too. The window where two civilizations are simultaneously in detectable phases and close enough for signals to actually arrive, that window might be extraordinarily brief. It's not that civilizations don't exist. It's that we keep missing each other in time. The silence forces a choice about how we interpret it, and that interpretation shapes what we do next. If the silence is a warning, if the dark forest is real, if the great filter lies ahead, then our priority should be caution. Develop defensive capabilities. Don't broadcast. Focus on survival. Recognize that advanced technology is dangerous and needs wisdom to match it. If we're pioneers, if we're among the first civilizations and others are still evolving, then what we do matters enormously. Expand. Establish ourselves on other worlds so no single catastrophe can end us. Set an example for the civilizations that will come after. If we're alone, truly alone, then we should cherish what we have. Protect Earth. Recognize that this might be the only place where life and consciousness exist in the observable universe. We don't know which is true. We might never know. But the silence is real. 60 years of searching, thousands of star systems examined, the entire electromagnetic spectrum scrutinized for signs of intelligence. We've found nothing. The universe, as far as we can tell, is either empty or full of civilizations that have learned to hide. And that absence, that silence, touches questions we've always carried. Are we special? Are we alone? Do we have a future? It forces us to confront the possibility that intelligence doesn't guarantee survival. That the power to ask these questions may come paired with the power to end everything. Every new exoplanet discovered, every atmosphere analyzed, every radio scan completed adds to our understanding. But the central mystery remains. We keep looking, we keep listening, because the question is too important to abandon. The silence of the universe might be the most important message we'll ever receive. We just haven't figured out what it means. There are 200 billion trillion stars in the observable universe. Most have planets. Billions of those planets sit in habitable zones where liquid water could